Hi, my name is Katharina Pöhlmann, and in this video I'm going to quickly talk you through my study looking into effects of cognitive load on vection and cybersickness using EEG to identify neurocorrelates of vection. So what affects cybersickness and vection? Many studies have looked into the effects of bottom-up processes on the experience of cybersickness and vection, such as stimulus size, speed, eccentricity, or direction. However, top-down processes have also been related to the experience of vection. So if vection requires attention and resources as believed, performing a cognitive task while viewing a motion pattern should decrease the experience of vection, and at the same time could distract the user from experiencing cybersickness. This is an example of one of our visual motion stimuli. Our stimuli either elicit self-forward motion, as you can see here, or self-leftward motion. And you can see that the trial starts with a fixation cross in the center field of view, which is then replaced by the rapid serial visual presentation task. The task itself always looks the same, just the instructions for the observer vary depending on the cognitive task condition. In the control condition, observers don't have to do anything, they just view the little monsters and indicate by button press whenever they experience vection. In the low cognitive load condition, they still indicate whenever they experience vection, but they also have one of these monsters as a target now and have to press a response button whenever they see it. In the high cognitive load condition, two of these monsters are now targets and they have to press the response button whenever they see either of them. The motion stimuli presented also cover different parts of the visual field. In this example, you can see a full field of view stimulus. This is an example of a central stimulus eliciting self-leftward motion. Participants not only performed the rapid serial visual presentation task while viewing the stimulus, but also indicated the button press when they experienced vection. They were instructed to press the button when the sensation of vection started and hold it in for the length of the experience. They could let go and press the button again as often as they wanted in each trial. After each trial, they then rated the sensation of vection in cybersickness on an 11-point Likert scale. And finally, here's an example of our peripheral stimulus. We based our EEG analysis on the analysis of Harker and colleagues from 2019. We looked at vection onset and ongoing vection time windows, with vection onset going from -500 milliseconds before vection onset button press to 1000 milliseconds after, and the ongoing vection time window ranging from 500 milliseconds after button press till vection offset or the button release. We compared the neural activity in the different cognitive load condition using cluster-based permutation analyses, hoping to find neurocorrelates of vection that reflect the differences in the subjective experience of vection for the three cognitive load conditions. So let's have a quick look at our behavioral results. We analyzed the effect of cognitive load on vection and cybersickness separately for the full field of view and the restricted field of view condition, and we found, as expected, that with increasing cognitive load, vection decreased in the full field of view condition. However, in the restricted field of view condition, vection actually increased with increasing cognitive load. And surprisingly, for both the full field of view as well as the restricted field of view condition, cybersickness increased with cognitive load. And now for our EEG analysis. Here we compared the low and high cognitive load conditions, and for ongoing vection we found stronger frontal theta and alpha desynchronization for the condition causing a weaker sensation of vection. In the full field of view conditions, participants experienced more vection in the low cognitive load condition compared to the high cognitive load condition, reflected here in a stronger desynchronization in frontal theta and alpha in the high cognitive load condition. Whereas in the restricted field of view conditions, participants experienced more vection in the high cognitive load condition compared to the low cognitive load condition, again reflected in a stronger frontal alpha and theta desynchronization in the low cognitive load condition. So in conclusion, our study found that mental task limit can affect vection and cybersickness, and it affects them differently. The effect of cognitive load on vection seems to also depend on the strength of the perceived visual motion and where in the visual field this motion is presented. Also, frontal and theta alpha activity could represent a neurocorrelate for vection magnitude that is modulated by cognitive load. Therefore, when developing a VR application that is eliciting vection while avoiding cybersickness, we do not only have to focus on what we present to our users, but also on what tasks they are performing and how cognitive demanding these tasks are. So finally, I just want to thank my great supervisors and technicians for helping out with this research and you for watching this video.